I never actually intended to study plants. In fact, my undergrad degree was purposefully in zoology, so I didn't have to study plants. But you never know, just goes to show you never know where life's going to take you. I'm going to talk about voltage-gated potassium channels again today. So we have a So I'll be focusing on the KV7s or KCNQ channels. I'll talk about some unpublished work at the end on the KV1 or KCNA channels. But as you can see, and you all know in this room, voltage-gated potassium channels are important for modulating action potential threshold, morphology, firing rates, cellular excitability. Voltage-gated potassium channels do have a nicely defined voltage sensor that that moves up in response to depolarization of the cell. This is communicated to the pore, which then opens and potassium diffuses out very, very rapidly, actually, according to the electrochemical gradient. So when these go wrong, for instance, by inherited mutations, such as in KCNQ2, we get inherited disorders of excitability. Usually, if they're loss of function disorders, will be hyperexcitability, such as benign familial neonatal epilepsy, as you see the mutations here, but more troublingly, encephalopathy, epileptic encephalopathy, which is a severe developmental disorder caused by mutations in KCNQ2, KCNQ3, and KCNQ5. So because of all this, there is a lot of interest in creating or discovering molecules that open these potassium channels to increase their activity and hopefully protect against these loss of function diseases. So as you know, retigabine was the first-in-class KCNQ channel opener for KCNQ 2-3 channels in the brain. It's a very effective anticonvulsant. It was actually taken off the market, removed in 2017 because of side effects unrelated to its neuronal KCNQ opening activity, but it is used in very severe developmental epileptic encephalopathy, again in pediatric patients, because it is effective, and in those cases the side effects aren't as bad as the disease. And then there's other derivatives of similar molecules such as ML213, and if you dock these, they bind to a tryptophan in the S5 of the channel, and other groups discovered and showed that if you mutate this tryptophan, the effects of those molecules go away. And then more recently, we found that actually, a bit of a surprise, that GABA binds to the same tryptophan. It activates KCNQ3 and KCNQ5 channels and KCNQ2-3 channels. And if you mutate that tryptophan away, so does the GABA effect go away as well. And we also found, perhaps unsurprisingly, gabapentin also binds, and it's quite a potent activator of KCNQ3 and KCNQ5 channels. And again, predicted by in silico docking to bind. Mutagenesis showed that when you take this tryptophan away, it doesn't bind anymore. And pregabalin actually was predicted to not bind, and accordingly did not activate these channels. So it's quite a lot of small molecule discoveries in and around this binding site. So we got into plants by accident because we'd also around this time found that voltage-gated potassium channels form complexes with some sodium-coupled solute transporters. And my postdoc in the lab, Rian Manville, was trying to discover new small molecules to mess around with the channel to see what it did to the transporter. It had been published and was understood that the rotlerin, or malatoxin as it's called, activates KCNQ1 channels but does not activate KCNQ2-3 channels. However, my postdoc Rian didn't believe the data. He tried it, and sure enough, it activates KCNQ2-3 channels. This got us thinking because malatoxin is from Malatus obesitifolia and other Malatus species. Malatus is used from West Africa across to Madagascar as a folk anticonvulsant. So we thought, oh, yeah, that's kind of interesting that Malatus opens KCNQ2-3. So we tried, we got the effect of malatoxin. We tried malatoxin as an anticonvulsant in mice, and it wasn't effective. So then we went back to the Malatus extracts, and another compound that was in there was isovaleric acid. Now, it's kind of a little bit similar to GABA, which we'd already found to open up KCNQ2-3 channels. So we tried isovaleric acid. It was predicted to bind to this tryptophan, and mutagenesis studies, which I won't show today for the sake of time, confirmed that. And when we add malatoxin and isovaleric acid together, you get this nice synergy of current increase compared to either one on their own. So all the mutagenesis studies and all the docking studies predicted that isovaleric acid and malatoxin actually sit in this binding pocket between the voltage sensor and the pore. And malatoxin actually kind of is predicted to hydrogen bond to this arginine at the foot of the voltage sensor, whereas IVA, isovaleric acid, as I said, is up there near the tryptophan. So this kind of really got us excited because we think this is the molecular basis for the anticonvulsant action of this folk medicine. When we gave the combination of molecules to mice, it actually was an effective anticonvulsant in the PTZ chemoconvulsant model. So then we moved on, and I'm going to whiz through these. We learned that cilantro and Mexican cilantro, or culantro as it's called, they were used as folk anticonvulsants in the Caribbean and Central America. Culantro, actually, the common name is fitweed, so it's used as a folk anticonvulsant. Long story short, we found that cilantro extract does actually open KCNQ2/3 channels. So we mashed up cilantro, we do a methanolic extraction, and then we look at 1 in 100. It opens KCNQ2/3 channels. We screened, I think it was 9 compounds that are well represented in cilantro, and found that E2-dodecanol, which is a fatty aldehyde, basically recapitulates the effects of the whole cilantro extract. And similar to what I was showing you for malatoxin, it's predicted to bind to this arginine at the foot of the voltage sensor by in silico docking and site-directed mutagenesis. Bore that out. And then what I don't show you for sake of time is that it's an effective anticonvulsant in mice, and other people had previously shown that cilantro itself was an effective anticonvulsant in mice. So moving from the neuronal channels to another KCNQ channel, quercetin is in lots of the foods that we eat, but it's most highly enriched in pickled capers. Actually, the pickling process increases the already rich content of quercetin in capers. So we were interested in studying quercetin because capers have been used in folk medicine quite a lot for a different range of disorders, not necessarily as an anticonvulsant, but in anti-inflammatory and other kind of indications. So it does activate Q2, Q3 weekly, but what was really interesting was that when you apply it to KCNQ1, it does this really nice thing where it increases the inactivation. So KCNQ1 channels, you don't really see the inactivation in the pre-pulse, but there's a little hook here, the famous hook, which is the recovery from inactivation. So there is an activation going on here, but it's kind of happening so slowly, overlaps the activation, you don't see it. When you add quercetin, it speeds everything up, so you see this really nice inactivation. Quercetin actually increases the activity of the channel down at these hyperpolarized voltages and consequently hyperpolarizes oocytes expressing KCNQ1. And then a similar molecule, rutin, which is actually made of quercetin, plus some other groups, doesn't do anything, so it's quite a specific effect. Unlike the other ones I've shown you, quercetin actually binds to the top of the voltage sensor. It's not very potent. The effects really get strong at about 100 micromolar, whereas E2-dodecanol, the EC50 is 80 nanomolar, so it's a lot more potent. Quercetin seems to bind to quite a lot of low affinity sites, so it binds to the voltage sensor. It also binds to this F340, which is a very interesting hub in the S6 of KCNQ1 that controls activation and inactivation, hence I think the effects of quercetin. And my student, Katie, who did this work, and I were very excited when our work got published in National Inquiry. You can't do better than that. So moving on to KCNQ5 channels in the KCNQ5 is in the brain, but also in the vasculature. And we were interested in understanding maybe we can find some small molecules that open up KCNQ5 in vasculature. The advantage of this is that you can relax the blood vessels by hyperpolarizing these channels. You can actually reduce blood pressure by causing vasodilation or vasorelaxation. So we asked the following question: does KCNQ5 opening explain the effects of antihypertensive herbal medicine? So throughout history, even before humans were Homo sapiens, we have a proud history in our human family of using lots of different herbs for medicinal and flavoring, even going back to Neanderthal man, and also Homo erectus is believed to have used chamomile and fenniseed for medicinal properties based on archaeological evidence. So we asked the question, we took 15 plants. The ones in red are the ones that have some kind of preclinical or clinical evidence of being vasodilators or antihypertensives. And then the ones in blue were kind of control plants. The results were really surprising. I'm going to show you the whole lot, and then I'm going to focus in on a few. But you might be able to see that if you look at this is the normalized voltage dependence. None of the blue ones do anything to KCNQ5 voltage dependence, whereas all of the red ones do something. So all of the antihypertensive herbal extracts activate KCNQ5, and none of the controls did. And there's just a close-up to see fennel seed is a huge activator of Q5. These are all 1 in 100, whereas things like tarragon and wheatgrass don't do anything, and they're not hypotensive or antihypertensive in preclinical or clinical studies. And you can see, one of the things we do a lot of this work in oocytes. It's really nice. You can look at the kind of unclamped resting membrane potential, and you can see that in KCNQ5 expressing oocytes, none of the controls do anything, whereas all of the antihypertensives open up KCNQ5 and hyperpolarize the cell membrane potential. We found that there's a molecule in sulforaflavescens, which is Kushen. It's a traditional Chinese medicine, and one of the 10 I showed you. There's quite a few molecules that have purported medicinal properties, but alaparin in particular was very effective at opening KCNQ5. The EC50 is 390 nanomolar. You can see it's I don't have Q1 up here, but it's also specific against that. So it opens up KCNQ5, but not the other KCNQs. So it's the first known selective KCNQ5 activator. This one, again, binds the arginine. If you mutate the arginine, even up to 1 millimolar, you don't see any effects. And there's the wild-type channel. And then our collaborator, Tom Jeps, in his lab in University of Copenhagen, Denmark, showed that alaparin is a KCNQ-dependent vasorelaxant. So if you can block it with linaperdine. If you don't block it with linaperdine, you get a very nice vasorelaxant effect. We're currently doing studies with this in a knockout rat line. We have a KCNQ5 knockout rat line. Really cool results, but I can't talk about them today. So in the final part of my talk, I'm going to talk about some mostly unpublished work. So moving on to KCNA1 or KV1.1 channels, we were contacted by a pediatrician, a pediatric neurologist in Madera, which is right in the middle of California, smack in the middle, and at the Valley Children's Hospital. And he had a patient, a little girl who had an L155P mutation in KCNA1, and she also has ataxia. And her mother also has the same mutation. That's where she got it from. And the mother was misdiagnosed initially with epilepsy, but she didn't have any epilepsy. She had ataxia. Ataxia, for those who don't know, is just a general umbrella term for movement disorders. Episodic ataxia 1 it's a movement disorder. You get slurred speech and other problems with the gait. And episodic ataxia 1 is due to KCNA1 mutations, usually loss of function. So we studied KCNA1 L155P. This is actually the first known EA1 mutation to be in the N-terminus of the channel. There's been a lot found all throughout the rest of the channel. Some of them also cause epilepsy. Some of them cause weird things like ataxia plus hypothermia. Sure enough, L155P function is reduced compared to the wild-type channel. These patients usually have one copy of the mutant and one copy of wild-type, autosomal dominant. If you were unlucky enough to get both, you'd have zero current, and then you have somewhere in the middle. So okay, that was cool. You know, can we fix these channels? So most of these patients are responsive to carbamazepine, which is a sodium channel inhibitor, but it doesn't actually directly fix the broken channel. It basically inhibits sodium channels to kind of balance things out. And we, in the past, had actually tried to make some synthetic molecules that could rescue episodic ataxia 1 mutant channels. So it's never been done before, and like many others, we got things that can activate the wild type quite nicely, actually. So here we did some in silico kind of docking, screening stuff with SwissDoc, and came upon some molecules that would be predicted to function in this way, and we got this 4TF-MPG. So it works quite nicely at opening KCNA1. It's actually selective. It doesn't open A2. It doesn't open Q2, Q3 either. The problem is when you get to the mutant, here's another mutant, E283K, that's responsible for episodic ataxia. It doesn't do anything. And we tried 4 different mutants. None of the ones we studied did anything. So that was a bust. So because we are very interested in botanical medicines, we thought, okay, let's turn to Native American medicine. So I've been really interested. I spent a lot of time going up and down California collecting plants that we used in Native American folk medicine practices. We searched and found that the Kwakwaka'wakw First Nation in what is now British Columbia actually had 3 ataxia remedies. And I don't understand why, and I have some theories, but because there were only 20,000 people at the peak of that First Nation, and ataxia is quite rare, but there's some reasons why they might have developed these. So they had 3. Nettles, which is Urtica dioica, bladderwrack kelp, which is Fucus gardneri, and Pacific ninebark, Physocarpus. So they're an amazing, rich culture, the Kwakwaka'wakw, amazing people. I don't have time to go into the history right now, but they're an incredible kind of First Nation to study. And there's still, sadly, there's only about 3,500 people who identify as Kwakwaka'wakw left. but they still have a rich history and culture. So we tried these extracts on our wild type. I'm not going to show you the wild type data because no one needs to fix wild type channels. So we tried it on E283K, and where all the synthetic molecules have failed, all 3 plant extracts work. So the wild type, so E283K right shifts the voltage dependence of these channels. So I've got the magenta is the wild type, and then the black here is the untreated mutant. And then you can see when we add the leaf extract or the kelp extract or the nettle extract, it shifts it to overlay. So really, and you can see huge effects, particularly here in the tail current. So incredibly effective. We tried 5 different EA1 variants. We were able to fix 2 of them. The other 3 were not fixable. We fixed the L155P to some extent. You can see not quite as effective as with this one, but you can see an increase with the 9-bark and with the bladderwrack kelp. Not so much with the nettle. And then the E283K is up here. So what's doing it in the extracts? Well, we looked at what the common compounds were in the extracts, and we found one that really stood out, gallic acid. If we look at our L155P mutation, we can see that gallic acid is fairly good at increasing currents in that channel. Up to 100 micromolar increases the activity. It's predicted to bind this isoleucine 182, and actually, when we did the mutagenesis, that was borne out. I won't show you the results right now for the sake of time. And the E2A3K, in particular, was really effectively rescued by just 1 micromolar gallic acid, and also tannic acid as well, which is also in those 3 plants. So we fixed the voltage dependence of that. So in summary, widely consumed food plants and botanical medicines can harbor some potent anticonvulsants such as E2-dodecanol. But E2-dodecanol, we're exposed to it all the time. It's a food flavoring. It's used in cosmetics, candles. So I wonder whether we're all being kind of baseline modulated by some of these compounds, and quercetin as well as in a lot of foods. KCNQ5 activation, I think you would agree, presents a unifying mechanism for traditional botanical antihypertensives. Alloperine, we were able to find from Ku Shen, is the first molecule reported to isoform selectively activate Q5, and then the last part I showed you was that, by looking back at what Native Americans did, we actually were able to discover that they'd already found some activators of KCNA1 that they used for ataxia. I'd like to thank Rian Manville in particular, who did a lot of the work that you saw today. Katie, who did the quercetin study. Angeli did some of the work on maltoxin as well. And Lily and Ryan and Maria did various support work or patch clamping or molecular biology. Tom's lab have been fantastic in partnering with us to look at evasive relaxants, as have the UCI Department of Chemistry Core, and Rich Sidlow at Valley Children's Hospital has been a brilliant partner as well, and we're studying more of his ataxia mutants. I would like to thank NIGMS sincerely and NINDS for the financial support that enabled these studies. The Susan Samueli Integrated Health Institute also gave me a scholarship to work on this plant stuff. The Kwakwaka'wakw First Nations, incredible ingenuity, and I'm glad we can kind of highlight the amazing work of those First Nations and other First Nations that we study. U.S. National Park Service and UC Reserve System give me permits so I can go to beautiful places like Muir Woods or Zizix in Mojave Desert or Santa Cruz Island here to collect plants and study how they work and how they can be beneficial. So thanks so much for your time. We appreciate it.
Really fascinating, Jeff. So I was just wondering, when we take some of these herbs in our diet, do we really get to the concentrations that are necessary to have these effects? And have you tested any of these on other ion channels at all?
Yeah, it's a really good question. So 2 questions. How much do we really get when we eat these herbs? And then what's the selectivity? Have you tested them on other channels? So firstly, if you drink a cup of tea, for instance, you get hundreds of micromolar doses of the polyphenols from tea within 10 minutes of drinking 1 cup of black tea. And we had a study actually that there's polyphenols in black tea and green tea that activate KCNQ5 as well. So yeah, in some cases you do. I know it's not always. The gallic acid I'm excited about. We just made a mouse model. We're in the process of making a mouse model of E2A3K so we can test out its efficacy in vivo. I didn't show you a lot of in vivo work today. We do have in vivo work for some of these. But gallic acid is available as a supplement over the counter. It's safe up to 5 grams per kilogram in my studies. So I think that could be one way to treat some of these forms of ataxia relatively safely. And I think you could dose those people quite highly and quite safely. So, but it's really important to look at the in vivo concentrations. I definitely agree. In terms of other channels, yeah, we occasionally do. There's only so much you can do. I think other people have mentioned screening programs where we can take the molecules to get them screened by a lot of other targets. We tried for some the synthetic compounds I showed that were actually based on glycine, believe it or not, originally. We tried those on a glycine receptor to make sure they weren't doing crazy things to that, and they weren't. So we do occasionally, but yeah, we're kind of limited in some ways the amount of channels we study. We have a compound now that I didn't want to show you today because it's super new and we haven't kind of protected it yet. But I think that one's going to be really exciting because it's a lot more efficacious than some of the ones I've shown you today. It's like causes a minus 60 millivolt shift in KCNQ3. So I'm really excited to talk about that in the future. But that's another compound that we found. That one, it does a lot of things to a lot of different proteins. So a lot of these are not selective, and even if you find sometimes that they're isoform selective within one family, they'll go and activate another channel. So it kind of does it. There's not a lot of rhyme or reason to it, as far as I can see. Yeah.
Jeff, back
Yes.
here. Back here, all the way here.
Yeah.
Hi, that was really nice. But I was wondering, to what extent could you comment on to what extent you can attribute a biological effect to, let's say, activation of KCNQ by the herbal medicine? So for quercetin, for example, it's very well documented to have effects on mitochondrial metabolism, biogenesis, functions as potentially as a raw scavenger and so forth. So and that's thought to be people generally think about that when thinking about the protective effects of quercetin. So to what extent do you think it's feasible to actually attribute some of these protective effects to channels versus other types of signaling?
Absolutely. So the question is, you find that these things activate a channel, but is that really causing the beneficial effect? So it's a really good point. I think with quercetin, I would not claim that at all. Quercetin was interesting for me because of what it did to KCNQ1 inactivation. But I think for something like E2-dodecanol, which activates at 18 nanomolar EC50, activates KCNQ2/3, I would say I strongly believe there's good evidence that acts as an anticonvulsant by opening KCNQ2/3 channels. With KCNQ5, so we were given a KCNQ5 knockout rat line by Ken Byron, very, very generously. We are studying, we were answering that question with that rat line, right? I can't show you the data yet, but we're giving those rats alloparine and looking at the wild type versus knockout, so we can separate the two. But it's a really important question, absolutely.
So, over here, Jeff. Over here.
Colin.
Yeah. So you're sort of dancing around the cutting to the chase on some of it, and I can understand that yeah, you're finding these effects. You don't know how much that's really what the biologic effect is of what eating these things is. But you said that the First Nations have ataxia. They eat those plants for that. So have you told that to the people from the Central Valley who've got the ataxia mutants, and do they say it does anything?
Right. Yeah, no, that's a really good point. So the question is, are you thinking about treating, right, people like, yeah. So with the First Nations, it's just with the Kwakwaka'wakw people, it troubles me that these are so rare that you wouldn't expect 1 in 20,000 people. It's less than 1 in 20,000 people get any form of ataxia. So why did they have three therapies for it, right? So I think the lifestyle. Back then, a long time ago, and a hunter-gatherer lifestyle or a hunter lifestyle meant that you had a lot more infections, traumatic brain injuries, that kind of thing. Also, those people would have taken hallucinogenic plants such as datura for their shamanic rituals, and datura can cause ataxia as well. So I was trying to think, like, why did they have so many ataxia therapies? But we have not gone back to them and said, okay, we've figured out why your therapies probably work, because I want to try them in that mouse model first to be really sure that you can enough of it get into the bloodstream to get into the peripheral nerves, say, you can, or into the brain even to fix ataxia, right? So one of the interesting things that the Kwakwaka'wakw people did was, I showed you that tannic acid was one of the molecules involved. Tannic acid is not good to eat a lot of. It like binds up everything in the stomach. It's actually used as an antidiarrheal compound. But what they did, they actually used seashells to slice the soles of the feet and then rub the plants against so they got it directly into the bloodstream, so they didn't have to ingest it. So I don't know, little tidbits like that make me think that they really knew what they were doing. And I before I go to these people and say, oh, we figured everything out, I want to try it in a mouse model. And the same for the patients. I'd like to show this efficacious before we start telling people, oh yeah, have a load of gallic acid supplement, see what happens, right? And also, there's, I noticed that you have to be careful. There was another publication that showed that some episodic ataxia is brought on by a diet rich in too many polyphenols, like it's brought on by chocolate, dark chocolate, and things like that. So I think you have to be very careful with the dosing. Not saying it's this gallic acid, but you have to be careful because they can be brought on by some of these molecules that are in plants as well. Yeah.